Hi everyone. My name is Leah. I Today I wanted to discuss computational linguistics and how it applies to the future of artificial intelligence. So why I kind of chose this topic is because I really like math and science. I'm a math and computer science major, so I think it's really interesting to look at how linguistics can relate to what I personally like to do. So I think, especially in terms of artificial intelligence, we kind of can see the uses of it widening in our everyday lives. So in like Siri and Alexa, so you can obviously see that this is pretty much like this is kind of where the future is headed, is through is towards like robots. And even in like movies like Star Wars and I, Robot, they've kind of already like anticipated this in the way. Like they were like, oh, robots that talk exactly like humans or we can talk to are kind of going to be the future of technology. So the question I was kind of asking is how can we use empirical linguistic data, which is kind of like which is data that we get from observation, to kind of tackle the more complicated parts of human language. So this is not only just because obviously we can just load a computer up with all the words and grammar that it needs, but it's still not going to be able to talk to humans because it doesn't have that semantic and pragmatic form of like a native speaker would have. So how can we get around that? How can we use um, research findings to apply that to robots and linguistic data? So kind of what I thought after doing a little bit of research is that the best way to do this is just by gathering as much data is kind of by having a robot companion, one that we can integrate into society, one that we would be talking to constantly, and one that would be essentially gathering as much data as it possibly can about language. Because language is so complex, it probably need some an artificial intelligence would definitely need to be able to know all of the possible aspects of language, and kind of formulate better what it how we use language, what our intentions are, or the different contexts, just like the human brain would be able to. So, kind of what my methodology was is I looked at a bunch of different or peer-reviewed art journals that relate to this field directly, which is especially computational linguistics, and kind of look like, well, where is science now, and looking at how can we make computers and robots speak exactly like humans do. So by looking at a couple just examples of stuff that I looked at, one of the ones that I found more interesting was using machine learning for garden path sentences. So we kind of talked about this in class. So a garden path sentence is when the beginning of a sentence, even though it's grammatically correct, kind of is hard to interpret once without reading it all the way through. So like as we're going through it, um, we don't know exactly what's going to happen at the end. So what this research group did is they looked at the user's previous interests and applied that to how exactly they would be able to interpret each little part of the sentence. So what we also discussed in class was sentence trees. So what it pretty much does is uses a set of statistical analysis to um, to go through these sentences. So, for example, like the main sentence they focused on was the complex houses, married and single students, and their families. So, while that's probably pretty like difficult to understand even for humans, what it did was it took keywords in the sentence and it also and so like houses are is related to single families is words like people probably use those words together more often. So what they did is they kind of looked at how houses was more frequently used, especially in that specific user, and kind of based its interpretation off of that. So like if we use houses as a noun more commonly and when we talk about families, then we can assume that it's being used as a noun in this sentence. So that's kind of what this did. You can kind of see one of the flowcharts that we used that they used down here is they said, like, is houses a noun? And it's like yes or no. And then it kind of from there can determine the different possibilities of the rest of the sentence using the same kind of algorithm. So what part of the sentence is a noun phrase? What part is our adjective? What part is our verb phrase? That kind of thing. And then at the end, as you can see at the end of the flowchart, it kind of checks if it was a success or not to see if it actually interpreted the sentence correctly. So I thought that was kind of interesting. It was kind of what I was talking about when in terms of how exactly we can use previous data to influence a learning in machines. One that can take what we kind of say casually without even thinking and kind of formulate that into something that a computer could understand. So another big focus in this field right now is the voice emotion recognition. So how can a computer determine the context of what we're talking about just through the emotion in our voice? And how can we classify these different emotions um, and relate them back to context? Because if you're saying something happy versus saying something sad or saying something sarcastic, it's like as a human, it's obviously going to have um, a different connotation, but if you're a computer, how are you supposed to know that without some kind of basis to go off of? So what these studies pretty much do is categorize our emotions. So like anger, disgust, fear, boredom, happiness, like that's kind of what this specific study looked at. And so what they do is they look at the pitch of the speech and the frequency of the speech. And as you can see, it ended up being pretty accurate. I mean, pretty accurate for where we are at right now. But as we as like what I was saying, if this were to have more data, then we wouldn't see as much of a lack of a recognition rate. If a computer had seen like millions of different people be sad, then the frequency would be, or the pitches, that would be a more exact number rather than a broader estimate of what exactly a sad pitch would sound like. So looking back at all of these studies, one of the biggest things I noticed is that their their analysis relied heavily on acted speech. So like that, the thing that I was saying is how can we rely on acted speech when that's not what we're saying every day? We speak in casual speech. So if we want to ever get to a point where we can talk to robots, where we can have a conversation with a computer, then we have to base our estimations, base our samples on actual real speech. So by doing this, we would create kind of like a bootstrap sample, which is an estimator that we use in statistics, in which we create an estimated population and take samples from that rather than our whole true population. And we would have to do this from a linguistic standpoint as well, because our true population is infinite. Like we've discussed in class, the amount of phrases, the amount of things that you can say with language, the amount of ideas is infinite. Like that's not something that we can give a computer because we ourselves as humans can't even comprehend that. So we kind of have to create our own sample from a limited set of data that we can have. But what I'm proposing is that we just increase this amount of data. If we can only get samples from a smaller population, why not just make this population as big as we can to reduce that sampling error? So I think that was like just one of the biggest flaws that I saw in these experiments, and kind of one of the solutions that I could see to be possible in the future. So in conclusion, I just think that when considering language acquisition in computers, the best way to fully capture the complexities of human language is to integrate empirical data collection into casual speakers' lives. So if we're the ones speaking this casually, if we're the masters of language, then why wouldn't we be teaching computers to talk.